So this week, there's not going to be many problems that I'm giving you because each one takes its own amount of time to do. Because the process of linear programming is a little bit more, time intensive. So you're going to be given chances to answer these questions, and then I will demonstrate how to go through and come up with an answer to that question using linear programming. As a side note, typically on a Keystone algebra test, you're not going to be asked to do all the procedure of linear programming. You'll be asked to do certain components of it, and oftentimes the test will lead you through those components to a certain extent. So you being able to do these questions in totality, you'll be able to practice all the parts of the process, and that will give you hopefully a leg up as far as doing it on an actual test when you're only asked to provide certain pieces of it. Either like situations where they might give you the graph and you're asked to interpret things from that point, or to come up with the graph that would help you interpret it. Typically that's kind of like where they will have you do it, whereas these are going to be asking you to do all parts of it all completely. So let's get to the first question. So an accounting firm charges $2,000 for an audit and $300 for a tax return. The table shows the times in hours required for staffing and reviewing. So based off of this, for an audit, it takes 100 hours to staff an audit, and it takes 12.5 hours to staff a tax return. To review an audit, it takes 10 hours, and to review a tax return, it takes 2.5 hours. The firm has 900 hours of staff time and 100 hours of review time available each week. Find the numbers of audits and tax returns that will maximize or bring in a maximum revenue. So they're giving you a number of things. Some of the things they're giving you are constraints, which are basically restrictions. And other things they're giving you is information about how to calculate the revenue, and the revenue calculation is what you want to try to maximize. So you don't really have a specific value for that at the time, but you do have information that will help you figure out what that maximum will be. So take a moment, see if you could try to figure out how to go about answering this question, and answer the question that pops up here, and then after you've given it your best shot, watch and review how the question would actually be answered. Okay, so again, there's a number of different parts to this. Obviously, I mean, you can see the revenue is going to be determined by the $2,000 for an audit and $300 for a tax return. So, that's where the money's going to come from. I just need to get an idea of, certain characteristics or certain combinations that are going to meet the conditions I have in this problem, and then look for the one that gives me the biggest amount of, revenue. So the two constraints I have are, obviously the staff time and the review time. There's only 900 hours of staff time and 100 hours of review time. So I just can't, or this accounting firm just can't just do, an infinite number or, whatever obscene number they can do. I mean, they have to have people that are going to do these things. So if I look at the constraints that they give me, staffing is going to be 100A, where I'm letting A represent number of audits and T represent the number of tax returns. 100A plus 12.5T should be less than or equal to 900 because, again, those are, how many hours are needed for each audit, how many is needed for each tax return, and, so the total number of hours used for staffing them has to be 900 or less because that's all they have to use. For reviewing, very similar. For an audit, it's 10 hours for each review to review each audit, and 2.5 hours to review each tax return. So 10A plus 2.5T should be less than or equal to 100. Now, oftentimes when you need to graph them, you might want to put it into a slope-intercept form, and this is what I got with these. And you're going to see that I use a graphing program. I'm not going through the step-by-step process of, showing how to go by graphing and finding the feasible region. You're going to see that when I produce the graph, it's going to already show the feasible region. If you need to, get more practice about how to do that, then please look at week 9's material where that's what our main focus was. So if I graph these and note the feasible region, so here's the staffing graph. Here is the reviewing graph. Notice I'm letting T take the place of X and A take the place of Y because I solved these for A because it was just easier to divide by 100 and divide by 10 in the long run than the other way around. And this is the region I got. And so basically the ordered pairs that are in this region are going to meet all of the conditions I have for staffing and reviewing, all the constraints I have. Now I want to find those that are going to maximize my revenue. So I'm going to look to see, okay, well, where's the corner points of this region? And it's the corner points that are usually your extreme points. You're not going to have situations that, if there's going to be a maximum, it's probably going to be on this outer edge out here. It's not going to be at 0, 0. Because if they do, if you think about it, you're not even going to test it. If they don't do any audits or tax returns, they're not going to make any money. So making no money should not be your maximum amount of revenue, because if that is your maximum revenue, then you're in trouble. So what I need to do, though, at times is figure out where these corner points are. Now, these are pretty easily done because they pass through nice points. This one passes through a point that's, not easily derived from this graph because, these are scaled to go by 5s, and this is obviously occurring somewhere between 5 and 10. So being able to solve systems of equations also comes in handy, and and you certainly should do that for these two, changes inequalities and equations to figure out what this intersection point is. If you do that, the corner points we have are 0, 9, which would represent no tax returns and 9 audits. This would be 8 audits and 8 tax returns. And this would represent 40 tax returns and no audits, just making them take their usual places. So, these are the ones I'm going to eventually test out. My objective function is, of course, the revenue. We mentioned the revenue before, but that's the objective function. That's what I'm going to use to figure out, which of these, ordered pairs are going to give me my maximum revenue, because I need a revenue function to let me know what that is. And so all I would do, with ordered pairs T comma A, I would plug in 40, 0 into this, 40 for T, 0 for A, and I would get $12,000 in revenue. If I do all audits, 9 audits, and no tax returns, I'd end up with $18,000. And if I were to do 8 of each, I would end up with $18,400. So obviously that is the maximum revenue. So the maximum revenue will occur when the firm does 8 audits and 8 tax returns. And as you can see, these things do take a bit of time to do. So make sure that you do spend the needed time on these things and do all the parts of them. So this first one, if you had some trouble with it, obviously, make sure that you note some things that you may have forgotten to do. And let's go to the second question here, so you could try the same thing. A fruit juice company makes 2 special drinks by blending apple and pineapple juices. The profit per liter is 60 cents for the first drink and 50 cents for the second drink. Or as they're going to say in their first drink, sometimes they say drink 1 and drink 2. The table shows the portion. So the ingredient, apple juice. The first drink has 30% apple juice and 60% and 70% pineapple juice, and the second drink has 60% apple juice and 40% pineapple juice. So there are 1,000 liters of apple juice and 1,500 liters of pineapple juice available. Find the numbers of liters of each drink that should be produced in order to maximize the profit. So since you're maximizing the profit, you know that the profit's going to probably be your objective function. it's, these percentages of the juices and these restrictions on how much apple juice and pineapple juice I have that are going to be your constraints. So with that in mind, take a moment, use the pause that play pause it gives you. See if you can figure out a way of coming up with your constraints, your inequalities, your objective function, come up with a graph, and then use that graph and the feasible region to figure out what would give you the highest possible profit, for these drinks, and how many, which of these drinks should be reduced, and how much of each. So, take a moment to do that, and then we'll go through it. Okay, so as we see here, I'm going to let X represent the liters of drink 1, or first drink, whatever you want to call it. And I'm going to let Y represent the liters of drink 2, or second drink. With these kind of descriptions, I could just graph this on a regular coordinate system without redefining the X and Y. I just have to make sure I know what X and Y stand for. Now, for me to figure out how much apple juice is being used, I mean, obviously the first drink has 30% apple juice, 70% pineapple juice. So if I take the number of liters of that first drink that were produced and multiply that by 0.3, that's how much of it would be apple juice. And if I multiply that by 0.7, that's how much would be the pineapple juice. Same thing with the second drink. If I take 0.6 times the number of liters of that drink I produce, then that's going to give me the number of liters of apple juice, in that drink, and likewise for the pineapple juice. I don't know how many liters of each, drink is being produced. Actually, that's what I'm looking for. So, but knowing that these percentages, based off of the information for apple juice, if I take 0.3 times X plus 0.6 times Y, that would give me, respectively, the amount of the number of liters of apple juice for the first drink, and the number of liters of apple juice for the second drink, and they should total somewhere at 1,000 or less. You can't produce more because we only have 1,000 liters of apple juice. Very similar for the pineapple juice. 0.7x plus 0.4y should be less than or equal to 1,500. So, so when I take the percentage times the number of liters of that drink, that's going to give me how much of that drink is that specific juice. And that's why I'm putting it in this order. These are my constraints. So that's what I'm going to graph. And when I graph it, making sure I'm scaling it accordingly to make sure it fits, this is what I get. My feasible region would be right here. And again, I'm going to be looking in this region. All the ordered pairs in this region are going to be situations where both of these conditions are being met. I want to find the one that's going to give me the highest profit. So what I first want to do is determine where these corner points are. Now, I have 0, 0 as a corner point, but again, I'm not going to even bother testing that one, because if you think about it, if we make 0 liters of drink 1 and 0 liters of drink 2, we're not going to have any drinks to sell. I'm not going to make any profit. So obviously, 0, 0 is not going to produce the maximum profit. So I want to determine where these intersection points are. Now, through calculations and solving systems of equations and what all, I would be able to determine that basically this point here is 0, 1,666.6 repeating, which is basically 2/3. So basically, that's saying here, if I make no drink 1 and 1,666 and 2/3 liters of drink 2, that's what I'm going to have here. Likewise, down here, this is me having 2,142.857. Now, it is a fraction. It's just one that doesn't repeat or have a nice pattern that it's really easy to write as a fraction. And in the end, you'd probably round off some of these anyway. So for this, basically this is saying if I do about 2,143 liters of drink 1 and no drink 2, this is where that corner point would represent. And this one here is 1,666.6 repeating, or 2/3, liters of drink 1. Remember, this is drink 2 in this one. This is that much of drink 1 plus 833 and 1/3 liters of drink 2. We want to see which one's going to produce the most profit. And most of the ones that you're going to deal with, I mean, whenever you see it, this intersection point out here is going to usually be the one. But don't just use that as your sole premise, because every once in a while they might throw one at you that, you make maybe so much more profit on one of these drinks versus another that it wouldn't be, that just making one over the other might be more feasible and a better thing to do. So, but I'm going to use the profit function to be that's my objective. That's what I'm going to use to determine what is truly going to be the maximum. So that's going to be 0.6x for 60 cents for each liter of drink 1 and 50 cents for each liter of drink 2. Adding those together will give me the profit. Now, plugging in the x and y values I have in these ordered pairs, this would give me a profit of $833.33 approximately. This would give me a profit of $1,416.67 approximately. And this would give me a profit of about $1,285.71. So as you can see, as I mentioned before, this one out here is the one that's going to give me the biggest profit. Therefore, to answer the question, the company should produce 1,666 and 2/3 liter of the first drink and 833 and 1/3 liter of the second drink in order to maximize profits. And that profit would be $1,416.67. So time to do one last problem for practice here. This one's going to be a little bit different because in this one you're going to be asked to find a minimum value rather than a maximum value, and it will sometimes happen that way. So the situation we have here is that a Pennsylvania fruit grower has 1,500 bushels of apples and divides them between markets in Harrisburg and Philadelphia. These two markets need at least 400 bushels and 600 bushels, respectively. And again, when you see that kind of description, that respectively means that since it's mentioning 400 bushels and 600 bushels in that order, in the previous sentence mentioned Harrisburg and Philadelphia in that order, then that means that essentially 400 bushels are going to Harrisburg at least, and 600 are needed at least in Philadelphia. The Harrisburg market pays the fruit grower $5 per bushel, while the Philadelphia market pays $10 per bushel. The fruit grower needs to make at least $12,000 in revenue. If it costs 20 cents per bushel to ship apples to Harrisburg and 50 cents per bushel to ship apples to Philadelphia, how many bushels of apples will the fruit grower send to each market to minimize shipping costs? So take a moment, go through the procedure again, find your constraints, come up with your objective functions, draw a graph, come up with a feasible region, and then from there try to see which combination meets all the conditions needed and also minimizes the costs for shipping. And then we'll go through it. Okay, so for this case here, I'm going to define x and y again. I'm going to let x represent the number of bushels being sent to Harrisburg, and I'm going to let y represent the number of bushels being sent to Philadelphia. Now this one's a little bit different than the previous ones also because this one has many more constraints to it. Luckily, they're only involving two variables, so they can all be graphed on a regular graphing region. But sometimes when you see linear programming problems, you might see ones that there's three different variables going on, and that would usually require you to start using matrices. So, and that's going kind of beyond what Algebra 1 would want you to do, though. So we're not going to get into that kind of thing. But I need to figure out, well, what's in this problem telling me there are constrictions or constraints, and what's going to be my objective function. Well, since we're looking to minimize shipping costs, all this information about shipping here in the middle here, we'll get back to it later. That's going to tell me, let's take that back. All this shipping information right here is going to be where my objective function is going to be coming from. These things are conditions that are being placed on this problem, either by the markets in Philadelphia and Harrisburg, how many apples the fruit grower actually has, and what kind of revenue he needs to make, and what each market pays him. Those are the things that are going to, dictate, what combinations would would work out in this instance and what won't. So as I go through this, the first piece of information is that he has 1,500 bushels of apples to divide between the two markets. So we know that x plus y should be less than or equal to 1,500 bushels. So, you know, I mean, so basically, if you add the amount of bushels he's going to send to one market and the number of bushels he's going to send to the other market, it has to total $1,500 or less. Now, the two markets, they have their own restrictions. The Harrisburg market needs 400 bushels or more. The Philadelphia market needs 600 bushels or more. So that's going to come down to x being greater than or equal to 400, y being greater than or equal to 600. There's one more restriction on combinations here. The combination of what's sent to Harrisburg and Philadelphia has to give him, the grower, a revenue of $12,000 or more. So this, since it's $5 per bushel for Harrisburg, that's 5x, plus 10y for the $10 per bushel in Philadelphia, that total should be greater than or equal to $12,000 in this case. So these are the four constraints we have in this circumstance. And so what I would do is I would graph these. So you can see the blue line here, which represents the combinations of bushels that could be sent to the two markets. The orange and the green lines represents at least 600 to Philadelphia, at least 400 to Harrisburg. And so you'd be in this region right here. And then this other one here, since we do have to have $12,000 or more in profit, that's going to put this line here. And the feasible region is this little triangle right here. So we have a kind of a really small window of possibilities here that are going to meet all these conditions to begin with. And it's out of here that I want to say, okay, what's going to be the minimum cost? So I'm going to find these corner points. Some of them are not that hard to find. I mean, and the way they happen to work out on this graph, since it was going by hundreds, it's kind of easy to read them anyway. But you would see like this first corner point's at 4,000, 1,000, which means 400 bushels being sent to Harrisburg, 1,000 being sent to Philadelphia. This one up here would be 400 bushels being sent to Harrisburg and 1,100 being sent to Philadelphia. And this one here would be 600 and 900. So as you go through these, it's like, okay, well, you know, these are my three possibilities. And some of them you can use some degree of logic. Like, for instance, here, if, you know, the 400, the amount to Harrisburg is the same for these, then obviously it's going to cost less to ship 1,000 to Philadelphia than 1,100 to Philadelphia. So you can almost eliminate this one without really testing it out if absolutely necessary. These two, on the other hand, and here's my shipping cost objective function, 0.2x plus 0.5y, 20 cents per bushel to ship apples to Harrisburg, 50 cents per bushel for Philadelphia. So it's down to these two really I'm looking at. If I use this objective function and plug in the x and y values we have in these ordered pairs, now you see I did try this one out too, even though I knew I really didn't have to. Between these two, though, this is $10 less than this one. So it would be cheaper shipping to do 600 bushels of apples to Harrisburg and 900 to Philadelphia. It would use up all the bushels he had, but it would certainly, you know, minimize the costs in the long run. So to minimize shipping costs while meeting all other constraints, the fruit seller should send 600 bushels to Harrisburg and 900 to Philadelphia. And that is the end of this video. If you have any further questions, please reach out and ask me. Until next time, have a good day.